This is Dr.BDY Sunil, Associate Professor, Mechanical Engineering Department, Institute of Aeronautical Engineering, Hyderabad. In today's session, we will be learning about the moment of inertia, radius of gyration, polar moment of inertia, theorems of moment of inertia. The course outcome of today's session would be calculate moment of inertia and mass moment of inertia of a circular plate, cylinder, cone, and sphere from the first principles. The topic covered would be moment of inertia, radius of gyration, polar moment of inertia, theorems of moment of inertia. The topic learning outcome would be understand the concept of moment of inertia and mass moment of inertia involved in practical engineering problems. First, let us see the introduction of the moment of inertia. The moment of inertia is the geometrical characteristics of a cross section of members. Right? Any members that is being considered in any construction site or any available load bearing capacity members, then if we take the consider the cross section of these members, that members bending characteristics would be considered as the moment of inertia. Then the strength and stiffness of the bending member depend on the moment of inertia of its section. The moment of inertia, also known as the second moment of area of a plane section about a given axis, is defined as the sum of the products obtained by multiplying each element of area dA by the square of its distance to that axis. Now let us consider a plane figure of area A here in the XY plane, and let dA be an element of the area situated at a distance x and y from OY and OX respectively as shown in figure. So that dA small elemental area we are going to consider, and we will be considering for the whole length. Then the moment of inertia of area A about x-axis, OX, that is OX is given as Ix. So moment of inertia would be represented with the term I, and the x represents here as the moment of inertia with respect to the x-axis, that is given as integral y square into dI, where integral y is the distance of that small elemental area considered, and dA is the area that is being of the small strip or small element that is being considered. The moment of inertia of area about y-axis OY, it would be given as Iy is equal to integral x square into dA. So overall, the moment of inertia for formulas for simple remembrance can be treated as area into distance square. So whenever moment of inertia is asked, you will be simply answering about that moment of inertia as area into distance square. You do remember this distance which you are considering is the distance from the reference axis. So always when moment of inertia is asked, you should definitely ask about the with respect to which axis. So the reference axis plays the key role here once again. Then coming to the radius of gyration, it is considered as the entire area is concentrated at a point on the lamina. Right? The distance of this point from the given axis of reference is called as the radius of gyration. Mathematically, it can be given as I is equal to A into K square. Again, this I is the moment of inertia and A is the area, where K is the distance of that area from the reference axis. So, we can write the same thing as K is equal to under root I by A. So, this K is called as the radius of gyration. Coming to the very important theorem, which is parallel axis theorem. This theorem is used to identify the moment of inertia of any lamina or of any object or body with respect to different axes. If at all we know the moment of inertia of any object with respect to one axis, and we need to identify the moment of inertia of that object with respect to any different axis, this moment of inertia can be identified using parallel axis theorem very easily. So the statement says that the moment of inertia of an area about any axis is equal to the moment of inertia about a parallel axis passing through its centroid plus the area multiplied by the square of the distance between the axes. So mathematically, it can be represented as IAB is equal to IG plus AH square, where IAB Ig is the moment of inertia about centroidal axis passing through centroid, that centroid of the object which is given. Okay, so moment of inertia with respect to the centroidal axis is termed as Ig. Then A is the area of the given figure, and H is the distance between the centroidal axis and the given axis. Okay, centroidal axis is the axis which passes through the centroid of the object, and that centroidal axis value I will be knowing. right? Whereas the given axis, nothing but the axis with which we need to identify the moment of inertia of that object is the given axis. And IAB is the moment of inertia about axis AB. Okay, that means that AB is the axis which we need to identify the moment of inertia with respect to that AB axis. Then the proof of this parallel axis theorem. Consider elemental area dA at a distance y from centroidal axis xx. Okay, so xx here, which you are seeing in the figure here, xx is the centroidal axis. That means the object centroid is somewhere here, and this centroid, this axis xx is passing through that centroid. Okay, and dA is the small elemental area which you are considering, and it is lying at a distance of y from the centroidal axis. Y from the centroidal axis. Please remember that. From definition, Ig, which is the moment of inertia of the centroidal axis of the object given, is taken as sigma dAy square. Sigma dAy square, where from figure, distance of dA from given axis AB is considered to be y plus h, right? The total height h from AB to the centroidal axis plus the total distance y from the centroidal axis to the strip element that is considered. So the IAB can be written as integral dA into y plus h whole square. That is area into distance square again. So it can be simplified to integral dA y square plus 2yh plus h square. From this we can write integral dAy square plus integral dA 2 yh plus integral dAh square. That is equal to Ig plus 2h integral dAy plus ah square. The term integral dAy here represent the moment of area with respect to the centroidal axis xx. Okay, this is equal to the product of area dA and the distance of centroid from xx axis. As the distance between the centroid and the xx axis is 0. Why? Because the centroidal axis is xx, and that means the axis is passing through the centroid itself. So the distance will be 0. Hence, integral dAy will be equal to 0. So overall, the value of IAB from the above equation can be given as Ig plus AH square. This is the equation of the parallel axis theorem. Using this equation, we can identify the moment of inertia of very, very complicated objects also. Then coming to the perpendicular axis theorem, this is very, very simple theorem which is also needed for identifying moment of inertia of complicated problems. If Ixx and Iyy be the moment of inertia of a lamina about mutually perpendicular axis x and y in the plane of the lamina, then the moment of inertia of the lamina about z-axis normal to the lamina and passing through the point of intersection of x and y axis is given by Izz is equal to Ixx plus Iyy. For understanding this, let us consider a figure here. Consider elemental area dA at a distance x, y from and r from y, x and z axis respectively. So this is the elemental area that is being considered dA, and the distance of this dA from x axis is y, and from y axis is x, and from z axis, this z axis is r. Okay, so these are the distances of the dA, elemental area dA from the reference axis. Now the moment of inertia of lamina about z-axis is, with respect to z-axis, how we can take that lamina's z-axis moment of inertia would be Izz is equal to integral dA r square. So, but we already can form the right angle triangle from this x, y and r, and we will be knowing that according to Pythagoras theorem, r square here, considering these three x, y and r, we can take a right angle triangle from this. Okay, and this is y, this is r, and this is x. So from this Pythagoras theorem, r square is equal to x square plus y square, or y square plus x square, right? Using this Pythagoras theorem equation, we can easily convert this r square is equal to y square plus z square as Izz is equal to integral dA y square plus x square. When you distribute this integral dA y square plus integral dA x square. But we know that integral dA y square is equal to Ixx and integral dA x square is equal to Iyy. that is the moment of inertia of the that elemental area with respect to x and y axis. So thus we can obtain the value of Izz as Ix plus Iyy. This is the proof of the perpendicular axis theorem. So this parallel axis theorem and perpendicular axis theorem both are very, very important while solving the complicated problems. The moment of inertia about z axis Izz is called polar moment of inertia. Okay, so whatever perpendicular plane, if you consider a two-dimensional plane, and if the moment of inertia of this two-dimensional plane with respect to the axis perpendicular to that plane should be considered, that perpendicular to the plane axis moment of inertia is called as the polar moment of inertia and denoted by J or IP. J or IP. So this concludes the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.